Swayam Prabha. Digital India. Educated India.
Okay, let's continue. Energy conservation. Again, in the case of the energy conservation, the equation plus minus is the same what we saw for one component, but we need to consider the energy that is linked to the mass interaction term. So, when we have evaporation condensation, okay, this means that when we have evaporation, we are going to transport energy with one component to the other one, right? Because we have a mass. We transport momentum, but we transport also energy. So the things are fine, but also we should consider other factors, because we said about the viscous dissipation. So one component is acting and producing shear stresses on the other component. But this is viscous dissipation, means also viscous heating. Okay? This is becoming complex. Or we may have a heat conduction from one component, from one phase to the other. Okay, so we have heat transfer from one phase to the other. It's not like let's say we wrote before that we have a heat flux coming from, let's say, the walls, like in the single phase. But here, let's say, bubbles may have a different temperature with respect to the liquid, or the droplets may have a different temperature with respect to the gas, and so on. Okay? Imagine, for example, to have a spray of a liquid at, let's say, 40 degrees, 50 degrees, inside the air at 20 degrees. So we have transport of mass, we have a mass interaction term, and we have energy because of the difference of temperature. It's okay? So the things are becoming, again, complicated because we have different conditions. So another point that is very important to say, and this is answering to one of the questions during the break, is that pay attention that the system is not in equilibrium anymore. So we are stretching let's say, the fact that the system should be in equilibrium. Imagine to have boiling, okay? But we have a phase change in general. So you have boiling, and you are considering the pressure of the system at a given pressure. Yeah, but locally, in time, the pressure is not the pressure of the system. Okay, it's changing because of the boiling itself. So in fact, what is happening is that the system itself locally and instantaneously is not in equilibrium. We are stretching the properties in a way that, we need to define the pressure, is fine, so we put the pressure. But in fact, it's quite complex, and it's becoming even more complex if you would like, for example, to simulate phenomena like flash atomization, as I said yesterday, when the negative pressure, and so on and so on. So it's becoming really complex what is happening. So, if you look at the energy equation in a single phase, this is what we have done before, okay? So, first of all, what we have now is that we need to write this equation for when we have different components, okay? In the case of the different components, we have a component n, we can write the total energy, of course, with the pedix n. That is saying that we can write this equation for the component n. Until now, it's fine. How is going to be, which kind of equation, energy equation we need to write? Okay, so in words, and then we need to translate in mathematics. We have the rate of heat addition to n from outside the control volume. What we have done before. So we have a wall that is heating the liquid or the gas. Fine. Or both. In this case is n, is one of the phase. Okay? Then we have the rate of work done to n by the exterior surroundings. Gravity, external forces, fine, no problem. Rate of heat transfer to N within the control volume. This is becoming a little bit more complex because it depends on the other phases. Plus the rate of work, not anymore heat, done to N by the other components because we may have drag. No? So then this is becoming complex. And this is equal to the rate of increase of the total kinetic energy plus the net flux of the total internal energy, because of course we are going to change the condition in terms of the energy. So these terms are very clear. We can write in this way if we consider the component N, the last two. And this is straightforward because it's the same equation that we have for the single phase, only that is for one component. Okay. The other one is a little bit more complex. Okay, the first one is the external heating. Okay, not difficult. It's a Q. It's a power that we are giving to the system. The second one is the work done to N by the exterior surroundings. Yes, it's okay, but then we are going to have stresses along the component, which is fine, no? And maybe we have the shaft work. But again, this is classical. We have the shaft work plus the stresses, tau, no? So again, it's something not unusual. It's something that we can understand. Then we have the three contributions that may be trickier. One is the heat that is coming because of the evaporation, boiling, condensation. So it's linked to the mass interaction term, QIN. And then we have the stress, the viscous dissipation due to the other component. And we are calling WIN. Okay? And then we are going to have all the stresses of the, let's say in this case, the continuum phases. Okay? So, of course, again, as we have done for the mass, the sum all over the components of QINN is equal to 0, because inside the control volume, the liquid is giving energy to the gas, and vice versa, but at the end, this term must be 0. Same things for the work, and of course, same thing for the internal exchange of energies. If we have a two-phase system, of course, one contribution is just equal to the other one with the minus sign. So what the liquid is receiving from the gas is equal to what the gas is receiving from the liquid, and vice and so on. So at the end, if we put all together and we sum up, we are landing with this combined phase energy equation, okay? Which is the equation that is saying how is, let's say, working with having more than one component. Let's pass to the 2. Because now we need to enter a little bit more. So, look at this equation. We already said something that is very important to define the forces, okay? Someone asked me during the break, how is the force? How the coupling between one component and the other, okay? This is a classical force expression, for example. It seems, wow. The classical force expression when we have two components, okay? When, for example, particle inside the fluid, okay? So, what is this? It seems complex, no? But because, of course, there are many terms that usually we don't have. You can recognize at the end, you can recognize the bulk force, the G, no? The gravity, like we have written before. So no problem. But there are other terms that are really more difficult to understand. So the first term is the Stokes drag. This is the force that is linked to the fact that we have a drag inside, as we have seen before. Okay, so for example, this is a drag felt by solid particles inside the gas or the liquid. okay? And the Stokes drag can be written in this form. It's 3 pi mu, so the viscosity, and then we have the dimension of the particle, u minus v, multiplied by a, let's say, a factor that can be written, for example, with this equation that is proportional, that is linked with to the Reynolds, 1 plus 0.15 Reynolds power to 0 minus, no, 0, 0.7, 0.687, okay, 0.7, 0.687. So this is the usual form. And of course, this Stokes drag is linked to the relative velocity of a particle with respect to the flow. Okay? Another point. Here I wrote D as a diameter, but imagine that things can be more complicated when instead of a spherical diameter, with a spherical particle, we have, for example, a cylinder, or we have something that is moving. Okay, so imagine, this is the simplest form. This can be much more complex, okay? But we have this form. Then we have the second term, is the acceleration of the surrounding fluid. So is the effect of the acceleration of the continuum phase with respect to the particle. If we are finding a way, what we saw before, no? If we have an acceleration of the fluid, the particle can go out because of the centrifugal forces, okay? There is an effect of the acceleration of the fluid on the particle that we need to take into account. Then there is another effect that is interesting. The liquid can accelerate. The particle can accelerate. The acceleration maybe are different because the mass are different. The density is different. Okay? So this means that we need to add the so-called added mass force. So there is another force on the fluid linked to the fact that we have particle that is accelerating, and the acceleration is different between the fluid and the particle. Then we have the gravitational and buoyancy force. In this term, we can have also let's say, the buoyancy, of course, because it's again related to the difference of densities, as we said before. And then we have this strange term that is the Basset history force, okay? And why this? Because a particle that is accelerating inside the flow may create vortices. So imagine to have a droplet that is moving, but is also accelerating. As you can see, for example, when you have the classical situation where you have a flow that is surrounding a ball, and of course, if the ball is moving instantaneously, we are creation of the wake. There is a wake behind, okay? So this means that there is an extra force linked to the fact that we have vortices. We have created vortices. And this is a force related to the past because the wake are formed for something that happened before. So before there is acceleration, we create the vortices, and we need to understand after a little bit of time which is the effect of the wake overall in the system. Did you get? Okay. And the form is that we have half of the d square multiplied by the square root of rho f of the density of the fluid multiplied by viscosity, pi. And then we have an integral from a given time, so from the beginning, let's say, to a given time. Then there is a kt tau that is so-called kernel, and then there is a derivative of u minus v. So is the effect, in fact, is not like the du over the t before. Is the derivative in time of the relative velocity now. So when you have the relative velocity, that is creating this kind of vortex. One can say, which is the difference between the Stokes and the Basset force, okay? The drag of the Stokes drag depend on the instantaneous velocity. So at the given time, you have a difference between the gas and the particle velocity. And this creating a viscous dissipation. Okay, so you calculate the drag. The other one, no, because it's not depending on the instantaneous velocity. Is the acceleration with respect to the relative velocity. So you don't have u minus v, but is the variation of this u minus v in time that is producing the drag. Okay, and this kernel, for example, at t minus tau, because if you are going very, let's say, back in time, this is becoming very weak in the sense that if you are going back in time, a lot of time before what is happening, the influence is very low. It's important to know what is happening, let's say, maybe few seconds or milliseconds before, not what is happening 1 hour before. So the heat transfer, this is about the force. Now we need to understand a little bit more about the heat transfer, okay? When you are heating up a particle or a droplet or a system in general, you have a characteristic time that is linked to the conductivity or convection, but also the thermal inertia, rho Cp of the system, okay? So this is the characteristic time of heating or cooling of a particle, a droplet, a bubble, and so on, okay? So again, when we are transferring energy from one phase to another, we can transfer energy by conduction, convection, and radiation. As I said yesterday, we are not considering radiation, okay? This is, however, very important, for example, when you are doing multi-phase simulation with combustion. Combustion is very challenging because not only you have different phases, but you have for the different phases you have an influence of the radiation, which is important, and it's not obvious to take care of this term, and also because you have different chemical species. So imagine now that what we wrote, this equation, when we write in this equation for the component n, we should split this equation for all the chemical species, and we need to have the closure equation for the chemical reaction. Okay? It's a course. It's a course. It's not 1 hour. Okay? But only, to give you the idea of what is happening. So we are writing this equation for the chemical species, and we need a closure equation that are saying what is happening to one species with respect to the other one because of the chemical reaction. So it's becoming quite complex. If you are reading a paper and with combustion simulations, you are understanding because maybe there is 1 page of equations. Because, if you start writing all the equations in the proper way, it's really very complex. You have all the possible combinations. So it's becoming very complex. If the velocity of a particle with respect to the flow, so the relative velocity is quite small, of course the dominant mechanism is the conduction. Forget about now for the radiation, but it's a conduction. So about the radiation, one can think, okay, it's only for combustion. It's not only for combustion because, for example, imagine to have very, very hot metal particles. So you produce, let's say, a metal spray, plasma spray, and so on. So you have particles at 2000 Kelvin, something like that are entering in the gas. Of course, the radiation is becoming important, even without a chemical reaction in this case. The point is that radiation is becoming important because depending on the gas that we have, the gas can be maybe transparent or almost transparent, but this means that there is a transfer from one particle to another, because in different position you have different temperature of the particles. Understand? So the radiation there becomes very important because the temperature is very high. Okay, only to say, because I was thinking, now I'm saying only chemical reaction, but it's not only combustion. It can be something like that also, thermal spray. Simulation of the thermal spray is considering also radiation. Now, for this, we are not considering, because it's, again, another level, okay? And we are not considering chemical species. But if the velocity is low, we have when the relative velocity is low, we can have this kind of expression that is say how much is the exchange between the particle and the gas. When we have convection, the things are getting complex. For example, I took this example because it's 2024, and I got this example because, again, multiphase flows is quite complex, and you see that the works, I mean, we are doing research. It's a field of research. It's not something that is established and everything is fine. So, for example, if we have a nozzle like that, and we are producing particles, and the particles are going, are molten, are liquid metal, for example, is going inside the nozzle like that. So convergent, divergent nozzle. So we are going to have a flow, and then we have different phase changes. We can have a solidification at the end. We are producing solid particles. And of course, in this case, for example, we have convection and radiation. Only to tell you that can be quite complex. So, a very nice way is, again, a very simple way is to consider, for example, the interaction between the droplet and the gas. And then in this case, we can use, or droplet particles, and the gas or a liquid. And again, we can come back with the relation that I showed you before with the Nusselt number. So we can use the relationship that we have seen before, where the Nusselt number was a function of Reynolds and Prandtl. So we can incorporate this kind of relation in order to calculate how much is the heat that is going from one phase to another. So the question is what we wrote before, but then we need to understand how we can calculate these relations. Again, on Thursday we are speaking about numerical methods, and we are going to, I'm going to tell you how can we deal with the different aspects, because there are different ways to solve the problem. Because one is considering the the dispersed flow. Each one, for example, when we are doing a VOF simulation of a spray, okay? So we are really going to understand at the interfaces, each one, what is happening. Of course, in terms of computational time, is very, very long, because we need to consider the single droplet. Another way is to consider the phase of the droplets in a kind of parcel, okay? So we are putting some droplets with the same diameter together. This is another way to solve these problems, okay? Now, today I'm giving you the general overview. Then of course, we are going to write the closure equations, because we need to understand then how to deal with the different terms. But this will be on Thursday. So yes, and then you can write this expression and so on. So it's very important, the temperature relaxation time. So so we have different times, and so on and so on. And now, another big chapter. This is for you. This is another big chapter. We saw that there is the term WIN. So the work that is linked to the mass interaction. The presence of the particles is changing the motion. So when you are changing the motion, you are having shear stresses. So there is a viscous dissipation. Okay? If the flow is turbulent, and we put in the turbulent flow, we put particles, what can happen? This is a big, big question now, okay? This is a big question. Okay. Let's see, put away something that is too complex for this course, non-Newtonian fluids. Newtonian, okay? Viscosity is the same. Put away situation where you don't have fully developed flow, so you have a nice condition. Again, we don't want to enter in the details, okay? Good. Because when you're dealing with, let's say, complex, unsteady motions, for example, when you have a pump and you're considering variation of the rotation of the pump, so variation of the pressure and so on, you may have segregation. So the particles, let's say what we saw before, no? We can create structures. We can have particles that are going in to the walls and so on, no? They are steady motion. Particle agglomeration, or coalitions of the droplet or the bubbles. So the droplets can coalesce, and so the bubbles can coalesce, and so on. So it's not changing the mass of the component, but it's changing the, let's say, the quantity in a given volume. Okay, so this is, of course, to consider. Okay, the particles in all the multiphase flows are having an effect on turbulence. This is the point. I said already, no? Okay. Now, if you want to study a little bit more this part, I put a paper that I enjoyed. Is a particles induced turbulence. So is the turbulence induced by the particle. So you have a laminar flow. You put inside the droplet or bubbles and so on. You are landing to have local turbulence. So you have a nice flow. But you put bubbles inside, like even a slack plug condition, like in a perceptible pipe. So you have bubbles going, everything is laminar. Wow, it's very good. Yeah, but behind the bubbles you have a wake. The wake is producing a vortex, and you may have kind of turbulent situation. So then, of course, there is an influence. Okay, so this is a critical review of physical concepts, numerical modelings, and experimental investigation. It's 2020, so it's quite recent. So imagine a spray. So you are injecting a spray, and you have gas that is going to be entrained in the spray, because the velocity is higher here, so the pressure is lower, so you have gas from the environment that is going inside, and then you are creating vortex inside, even if the air was completely still at the beginning. So, completely still, we are injecting the sprays, we are completely changing the motion with a lot of vortices, so we are creating turbulence. And the turbulence can even, let's say, at the beginning, if it's completely unsteady, the turbulence can create a situation where we can change the condition of the spray, or let's say of the atomization. And for example, if you look at the second result here, that is in the paper that I cited, this is the dimension of the particle with respect to the turbulence length scale, no? The lambda, no? And here is the percentage change in turbulence intensity, okay? So, as a function of alpha p rho f over rho v. And as you can see, there are different data that are a little bit scattered. So this means that even with experiments, it's not clear what is happening. It's very complex. But it's very clear that we have an influence. And the influence is depending also on the dimension of the particles. And even think about the fact that if the particles are not spherical, it's even more complex because we have also rotational mechanism. So we have, for example, if we have sticks, strands, and so on, these strands can evolve, and then, of course, they can change completely the local turbulence again. So the system can be quite complex. So there are 5 key factors that are, let's say, explaining what is happening. One is the so-called surface effects. Is the particle size normalized by the length, by a length scale. So this dp over lt. Then we have inertial effects. So we have the different velocities for the particle and the continuous flow. We have the response time, the particle response time, or the so-called Stokes number. Maybe I can say something later on. which is also very important, because it's the answer to a change in of the flow velocity, so the acceleration. Loading effect, how much is the quantity of the particle inside, and the interaction effect, because also we have particle-particle, we have collisions, and we have particle wall, and so on. Okay. LT is the turbulence length scale that can be written in terms of K and epsilon. And this is quite useful because, of course, K epsilon, for example, is a classical model to describe turbulence in numerics, so we can use these values. Where K is the turbulent kinetic energy, and epsilon is the dissipation rate. And then there is a constant, which is, for example, for the K epsilon turbulence model is 0.09. The response time is the classical response time is the rho of the particle, density of the particle, multiplied by dp squared, divided by 18 times the dynamic viscosity. Look, if we consider alpha, the volume fraction, this is interesting graph from Ergobashi. So it's true that below a given value of the volume fraction, so when we have very few particles, very few, okay, there is no effect. So there is no significant effect. There is an effect, but it's negligible. There is always an effect. But this effect is negligible below a given value, alpha p, okay? After, we have a second region here where we are going to have more particles inside, and we have the so-called two-way coupling regime. So, in fact, there is a influence from one component to another. However, there is a point. Depending on the time of the response particle time, and this is, let's say, the kind of turbulence time, depending on this time, the response of the time, we may have the situation where the particles are enhancing the turbulence, and the situation where they are attenuating the turbulence. Okay, so if the time of the particle, of this kind of response time of the particle, is small, okay, we are going to have this effect of attenuation of the vortices. Okay, so because in fact the particles are following somehow the flow. Okay, so imagine that you have some turbulence and the particles are entering, and so in the vortex, and they are following the vortex. Since you are adding a mass to the vortex, in fact, you are slowing down the effect. So you are dispersing because you are creating stresses. So somehow you are smoothing down the turbulence effect. But on the opposite side, if we are going to have the particles are going inside, and they are not following, but they have a little bit more inertia, they may be stretching the vortex, they are creating even more vortices. And so they are increasing the turbulence, not decreasing the turbulence level. Okay? And then we have another point, so-called four-way coupling regime, when we have a lot of particle collisions and they are becoming dominant. So, because imagine when you have a fluidized beds with a lot of particles and so on. The fluidized bed maybe is not a good example because it's a homogeneous flow, but let's say with a spray. So you have really a lot of things happening when when we have a dense spray, because we have coalitions of the droplets and we have change of the volume of the droplets and so on and so on. As I said, homogeneous flows are very important because in this case we can treat the multiphase flows as a single flow. This is single phase, sorry. It's a single phase flow. And this is quite useful. The things, what is important is that in this case there is always, we are thinking that the relative motion of one component with respect to the other is negligible. We can neglect. What is changing? Are changing the properties. the viscosity, the other is changing, and we need to change it to put an average viscosity. Because, of course, if we have a lot of more small particles, this is going to change the average viscosity of the system. But we can survive with this. So we can consider the system also in this term. Okay. One thing that is interesting, for example, is not changing only viscosity, but for example, another property, this is interesting for the compressible flows, is the sound velocity, the velocity of sound. This is changing with the presence of the particles inside. This is the sonic velocity, for example, as a function of particles inside the system. And this is interesting to know. But again, in a homogeneous condition, what we can do, again, look, the density is becoming an average density. No? Again, see? So in a homogeneous flow, when we have a lot of bubbles, a lot of small bubbles, a lot of small droplets, for example, a classical example is the aerosol. Aerosol means having very small droplets under 5 micrometers in a flow. So they are following the flow, and there are a lot of these small droplets. So we can use the volume fraction in order to define which is the average density of the system, the average heat capacity, the average viscosity, and so on. So this is possible to do. Okay? In this case, for example, you have even with a compressible flow, you have even an average of the density that is giving the correction for the sonic velocity. For example, this is happening when you have a situation like this one, and what is interesting, for example, is that the sonic velocity of a mixture is much smaller than the sonic velocity of one of the components. So if you have, for example, air and water bubbly mixture, you have the sonic velocity is much smaller than for the water and for the gas. And here you have, for example, a condensation front. This is a typical, this is a very nice image from a shock wave that is produced by a jet. But it can be even that we don't have, let's say, we are not going to have a shock wave. It's really the fact that we have very low, a front of very low pressure, and this creating condensation, and then is producing. Sorry, I said low, high pressure, and is producing droplets. And then we have the sprays. There's a big chapter, of course, in multiphase flows, as you can understand. And I'm giving this, I'm going to come back to sprays a little bit also on Thursday when we are dealing with interface, because I'm giving to you this part as a kind of supplementary material again, okay? But what's important to say is that we didn't consider until now the surface tension. Of course, when we are dealing with liquid, we are dealing also with the surface tension, okay? And but because on Thursday I'm going to speak about that. I'm going to define the surface tension. I'm going to define the effect of surface tension in the flow, and how can you incorporate this surface tension inside the equations, okay? Otherwise, it was too much for today. It's already with drag and buoyancy and so on, it's already too much in 1 hour. So, but then what is important is that we are going to explore the effect of the surface tension. Of course, in liquid sprays, the surface tension effect are very important, and sprays are really very complex. Are dispersed multiphase flows, maybe a reacting sprays, means that with the combustion, for example, and is one of the most difficult simulations that you can think. It's really very complex. We have evaporation, we have condensation, we have coalitions, we have everything. If you start thinking to a spray, you can put everything inside. And for the dispersed flow, for the dispersed multiphase flows, it can become really very important. Also because, another point, the droplets may have different diameters. We wrote the equation with a D, But imagine that now we have not only 1D, but we have a distribution of the emitter in the spray. So it's becoming really very complex. But of course, is a field that is very important for combustion, propulsion, spray drying. We have many applications, industrial applications that are related to the sprays, electro sprays. Here, I put this example because is an example at the nano level. So how to produce nanoparticles, no? Very small particles. Painting. And here, for example, is interesting. My colleagues at the University of Stuttgart, I know them since a lot of time. Imagine that in 1998, I visited Daimler-Benz in Ulm, the research center of Daimler-Benz in Ulm, and the guy, the name was Chris Angad, was the head of one department of the research there, and he was thinking, maybe we can think to simulate the entire process of painting, no, of the car. Okay, it was in 1998. With the computer at that time. But he had this idea, maybe we can do something. In fact, in Stuttgart, they are working a lot on this topic. And here, for example, we said about the force. Well, we have another external force. When we're speaking about electrostatic painting, we are thinking about the effect of charges inside the spray. Because the spray is charged, and so we have an extra force to consider in the equations. Of course, usually what they are doing is that if you consider this, then you need to simplify something else, because otherwise it's becoming too complex, but it's interesting to know. See, this is an example where the force is not only G. There is another force acting, and there is electrostatic force. Then we have pesticides, so sprays. Asthma sprays, deodorant sprays, and so on. And of course, everything is linked to the fact that the physics of the primary atomization is really a very difficult and complex one. And okay, of course, there is another course. I'm doing a course called LEADERSP, where we are speaking about that for 5 days. So, but I'm giving you these slides as supplementary material. If you are interested, someone is working with sprays, maybe it can be interesting to understand what is happening there and the different form of the primary atomization, velocity effects, and so on and so on. So also here, for example, in a nozzle, you may have a cavitation inside the nozzle. So again, you have another effect. And only to say, and I finish with this one, with this sentence, imagine that only until 10 years ago was almost impossible to have a simulation of the sprays from the nozzle to the final effect. So the simulation of a spray was what is inside the nozzle until the nozzle, and then we started with a given situation at the nozzle, and we propagate the solution to understand the cone angle, the droplet movement in the space, and so on. And but it was very difficult to put the two things together. Now we are doing this. Now we are able to have the simulation, the CFD simulation that is starting from inside the nozzle, maybe with cavitation, intermittency, and so on, and is producing the jet at the end with a breakup. It can be an aerodynamic breakup, instabilities, and so on and so on. So, but it's really very recent. It's not, we are not speaking about 50 or 40 years ago, but we are speaking about 10 years ago. Okay, look at the time, guys. Turn your head and look. Okay, so I'm staying here for 1 hour. If you have any question, please ask me. This is the time for you to ask me and to prove if I can say something or not. I'm not sure. Okay, thank you so much. And